Three-phase power factor correction. In this presentation, we're going to look at the steps required to power factor correct an inductive three-phase load, as well as look at the differences between a Y versus a delta capacitor bank. Well, first things first, we need to know generally what the steps are, the procedure in order to power factor correct. You'll notice that it is very much unchanged when compared to single-phase power factor correction. The only difference will be finding the value of S, Q, and P requiring our root 3 equations. Now, the first step that we need to do in order to evaluate and solve for a different power factor is to first calculate the original load before power factor correction has taken place. And so that usually requires us to calculate the S, VA, Q, VAR, and P watts of the load. The second step is then to build a new power triangle with the P or watts of the inductive load and the new power factor. So in this particular situation, we are wanting to power factor correct the motor to 0.9. So the triangle would have the 0.9 power factor. The third step is then to take the before power factor correction VARs and subtract the after power factor correction VARs. The value that is left remaining is the new required leading VARs, and this effectively is the size of the capacitor bank that we need to install. Well, let's then apply this process to this example. 208 volt, three-phase, 15 amp, a power factor of 0.7, and we're going to power factor correct this to 0.9. First thing we need to do then is to calculate all of the values for our motor before power factor correction. So what that means is that we probably should calculate everything on a power triangle. Now, I filled out the entire power triangle, but what I started with was the 0.7 because I know it is a 0.7 power factor motor. I then took my E line, I line, root 3, and got my VA. As soon as I had my VA, I placed it on the hypotenuse of my triangle, at which point it is then up to me which methods I then choose to determine the watts and the VARs of the triangle. My preference typically is to utilize this formula here. Now remember, when we're just dealing with the triangle, there is no root 3 that I need to apply when I'm going from VA to watts to VARs. It is only when we are determining the initial value of VA from the line voltage and line current that we need to use root 3. So I've taken my S total, I multiply it by my power factor, which is 0.7, and I get 3782.79 watts. At this point, I choose typically to use Pythagoras in order to determine what the total amount of VARs is for this particular motor. And so I use Pythagoras, S total squared minus P total squared, whole square root thing, 3859 VARs. So this is the entire motor before power factor correction has taken place. What we want to do now is determine what some of these values are going to be after power factor correction. And remember, we already know what it's going to be power factor corrected to because it is stated in the question at 0.9. First thing we want to do is build ourselves that new triangle. And the new triangle is a much smaller angle because the power factor is 0.9. The only value that I bring over is the watts. After that, I can then calculate the remaining two sides of the triangle. The way that I choose to do this is to first calculate the S total when I have the power and the power factor and take the power, divide it by the power factor to immediately gain my VA. Then I'm going to calculate my Q total, and typically I'm rather lazy, which means that I prefer to calculate my VARs using Pythagoras rather than cranking out what the angle is and doing sine of the angle. Once we've done this, our final step is then to determine what is the amount of leading VARs that we need in the system to power factor correct the motor. Now remember, this is going to require that we take the old VARs, which are over here, and subtract the new VARs, which is the remaining VARs after power factor correction has taken place. What we get is 2027.14 VAR, and that was determined by subtracting these two values. And as stated before, this is now the capacitive VARs required for my capacitive bank. Now that's kind of half of the answer right there. What about the bank itself, the capacitor bank? How are we going to assemble that? And so that brings us to another topic. Well, when we size a three-phase capacitor bank, we kind of need to know what form of capacitor is being used. There are three-phase capacitors and there are single-phase capacitors. Three-phase capacitors have 3 terminals. And so to size the capacitor, it's quite simple. Total leading VARs equals the minimum kVAR rating of the capacitor. However, when you get into larger power factor correction applications, the three-phase capacitors are not large enough. And due to that, we need to then size individual single-phase capacitors. Now, remember, when we are dealing with when we deal with transformers and all sorts of other types of applications, all we need to do is take the total, in this case, leading VARs, and divide it by 3. When we have that total leading VARs, it gives us the minimum kVAR rating for each of the individual capacitors. And it doesn't matter if our capacitive bank is going to be delta or Y, the kVAR rating will be the same in both situations. So why would it then matter if we do Y or delta? Well, let's take a look at our example again and see how this would then apply. So we've already determined that for our particular motor, we had just over 2,000 capacitive VARs required for power factor correction. Now, if we were to size and determine the required bank based on it being delta, well, delta 208 volt line, which would then mean that each capacitor had 208 volts across it. We would divide the total by 3 to get the individual VAR rating for each of these 3 individual single-phase capacitors. I then place that into a bit of a chart where I have the Q VARs, E the voltage. If I divide those two using just one of our basic power formulas, we get 3.24 amps. And that would be equivalent to the phase current that would be right here, 3.24 amps. I can then take it a step further by using Ohm's law. 208 divided by 3.24 amps will then give me 64.19 ohms. Now, the line current for this installation would be 5.61 amps traveling right here. If, on the other hand, we wanted to do a Y connection, well, a Y connection will have exactly the same line current because it is going to provide the same amount of leading VARs. However, the voltage rating of each of the capacitors will be slightly different. Again, we take our total, divide by 3, get 675 and change VAR. VARs, voltage, remember they're connected in Y, so even though we have 208 volt line, it's 120 volt phase. 120 divided by 5.63 amps gives me 21.31 ohms. And again, drawing your attention back, the I line equivalent to the I phase is exactly the same line current that we would expect if we were to connect it in delta. So other than the voltage rating, is there really any difference? Well, in fact, yes, there is quite a difference between these two installations. These are 120 volt rated capacitors. These are 208 volt rated capacitors. These capacitors need to be able to handle 5.63 amps, which is quite a lot of current when we compare it to these ones, 3.24 amps. The golden rule in electrical is that the cheaper alternative will likely be chosen. And when we're looking at the difference between these two capacitors, the capacitor that has to carry the most current will be the most expensive, because the only way we can account for more current is to make the innards more beefy with more copper in order to handle the current. Whereas voltage is much easier to accommodate simply by expanding the spaces between the conductive metal components inside a piece of equipment. So let's take it that step further and determine what the microfarad rating will be for each of these individual capacitors. That microfarad rating is going to require our XC ohm value, which is different for each one of these different configurations. We can see here that for the Y installation, each capacitor, 675 var, 120 volt, and 124, this is meant to be a microfarad. Whereas on the Delta system, each capacitor is 675.71 var, rated to 108 volts, and has a microfarad rating of 41.32 microfarads. Well, with all of this and a direction of how we approach these different types of power factor correction bank configurations, let's look at a slightly larger installation and see if we can't power factor correct this one also. This example has two individual motors, and these individual motors are wound slightly different. One of them is wound as a delta motor and one is a Y motor, but it doesn't really matter. And the reason it doesn't matter is because all we want to know is the amount of VARs and VA and watts that each one requires. They're both connected to 208 three-phase 60 Hertz system. One's got a power factor of 0.5, one's got a power factor of 0.65, both fairly low. One's a 20 amp motor, one's a 40 amp motor, and we want to correct the system to 0.9 power factor with a delta capacitive bank. All right, well, first step that we need to execute is to determine all of the original values for this equipment before power factor correction takes place. That will necessitate the need for some power triangles. So motor one, we want to know what the S, the VARs, and the watts are. And so the first place that I start always is here. I calculate the S total for my motor by using the line voltage, line current, and √3. Once I have that, I then work on to the power, and the power value is S total times the power factor, giving me just over 3,600 watts. Then I choose to use Pythagoras, and in doing this, I get a value of VARs of 6240. Well, let's take a look then at the second motor. The second motor, again, I need to know all of the individual values for it. And I'm first going to start with determining the VA. The VA of this motor is the line voltage times line current times √3. The power total is going to be the S total times the power factor, giving me 9366 watts. And finally, Q total is simply going to be the VARs value here when we take our Pythagoras total of these two sides of the triangle. Now notice I put a plus symbol in between, and that's because we are going to determine what the total watts, VARs, and VA is of the entire installation before power factor correction. In order to do that, we build an entirely new power factor triangle, and we can see here that it is combining the watts of both motors for 12,969 watts and the VARs of both motors, which is giving us 17,191. I use Pythagoras in order to determine the total VA of my circuit, and then I can divide my watts by VA to get my power factor. So here's the math that I've used. Power 1 plus power 2, Q1 plus Q2, total VA, and finally the power factor, which is 0.6. Now at times we're going to be asked, well, what was the original current on that system with the original motors? Well, let's take a look and see what the current value would have been. We had two motors. The source was 208 volts, We had 20 amps on motor 1, 40 amps on motor 2, and I've only indicated the current on one of each of the 3 line conductors, and that's simply to simplify visually what we're looking at. Understand that all 3 of these would carry 20 amps, all 3 of these 40 amps, and all 3 of these 59 amps. I line is equal to S total over E line times root 3, which means if I use the original VA from our previous calculation and divide it by 208 times root 3, we end up with 59.77 amps. So that's the original current that would be flowing from the source to supply these 2 motors. Well, the next step that we're going to have to do is to determine what the total is for the entire circuit after power factor correction. So that means we're going to have to build a new triangle, and we're going to take the watts of the original circuit with us. So that's going to look somewhat like this, and I try sometimes to sketch the triangle a little bit smaller so that I can see visually that it has shrunk. This value here, 12,969.59 watts, is from the original triangle. I then applied the power factor, which was given to us in the question, and I divided that to get my new total VA. So power total divided by power factor. In order to get the Q total, I used my Pythagoras S total squared minus P total squared. Now what we're going to do is take the before power factor correction VARs and after power factor correction VARs and subtract the 2. This gives us just over 10,000 VARs, and that would be the total required leading VARs for my capacitive bank. Now remember, in the question, they said we have a total leading VAR requirement that's going to be supplied by a delta bank. And this delta bank is going to be individual single-phase capacitors. That means I'm taking my 10,000 VAR dividing by 3, and I get just over 3,600 VAR for each individual capacitor that I will assemble in a delta configuration. So let's take a look at what the ratings will be then for my individual capacitors in my delta capacitor bank. So here's my delta bank. We already determined that it's going to be 3636.5 VAR. I know that it's a 208 volt 3-phase system, which means when I apply the voltage, I get 17.48 amps. Now remember, the VARs here was the VARs for an individual capacitor. The voltage was the voltage across the individual capacitor, meaning that the current that I calculate is indeed the phase current flowing through a single capacitor. I'm going to calculate the ohm value because that will be used to determine my microfarad. And remember, I'm doing 1 divided by 2 times pi times frequency times the ohms of XC of that capacitor. Always convert it to microfarad. That is the most common measured value. All right, well, what about the current that we see here? How many amps am I going to see on the line? And the line current that we would expect to see on this, well, we can take the phase current and multiply it by root 3, but I know there are many other ways that we could determine this. Perhaps we use the total leading VARs and do a 3-phase calculation with that. Either way, we come out with a value that is just over 30.27 amps. And this then is the line current of our capacitive bank. All right, so now everything together, what does the new system look like? Well, the new system with the capacitive bank installed will look like this. We've got our original 2 motors that still operate at poor power factors, 0.5 and 0.65. The capacitor bank is delta connected and connects to the line conductors supplying 30.27 amps of leading reactive current. The 40 amps is the only amount that continues to be supplied by the source itself. And remember, this is quite a substantial drop from the original 59 amps. The way I determined that was by using S total in my after power factor correction triangle, which was just over 14,000 VA, and using my three-phase I-line current calculation to determine the 40 amp value.